we'll do a tutorial on object detection today. So for this, we'll initially begin with image classification. So I think we all understand what the task of image classification is, right? So it's basically that you have some images, you have some appropriate labels for these, and then you pass it through a model, something like a CNN, and you expect it to predict some labels for those classes, correct? I believe all of us has trained a CNN to do like basic tasks like cat dog classifier or a MNIST detector, like handwritten digit detector. Anyone who has not done this, I'm assuming this is like the prerequisite and everyone has done it, right? Okay, cool. So we'll do this task, right? Now assume you are an image classifier and you can only predict cat or dog, right? Assume that you only predict cat or dog. What is this? Cat, right? What about this? Cat or a dog? Dog. Is this cat or a dog? You can say one. You are not allowed to say two things. Cat or a dog? Who wants to volunteer? What is this? No, both is not an option. But why? Why? Okay, but is cat not there? Okay, okay. So that's the issue with the classification. So classification is not enough. So basically classification tells you what an image has. It does not tells you where it is. So that's where object detection comes into play. You have to identify what the image has and also localize it, where it is. So basically something like this. So these are some of the use cases just to motivate why we may want to do an object detection. So we can identify, let's say for the manufacturing part, we can identify defects. In retail, we can identify if there is any missing portion, like, okay, I'll need to stock some food here, like, यहाँ पे लेस के chips रख सकते हैं हम, right? I'm a farmer, I want to count cows, right? So I can count, okay, this is Bessie, this is Helena, maybe something, right? Do I have even the appropriate number of even cows or not? Or maybe the worst one, like they can read your, what is this? Your license plate and then you will get fined, right? So now for classification, you ideally need two things, right? You need an image and you need a label for it, and you can try doing something with that. What do you need for an object detection? So any guesses? What do you need for an object detection? You want a bounding box, you also want a class for that bounding box, right? So how do you make a bounding box? To make a bounding box, you ideally need 2 points, the top left corner and the bottom right corner. And you can make a box out of it. So to make a box, you can have the top left corner X, Y. And if you're given width and height of that box, you can draw out the entire box. Similarly, if you're given the top left and the bottom right corner, you can again make the box. If you're given the center and you have width and height of it, you can again make a box. So how do you make a box? For the center one, you take the center minus W by 2 plus W by 2. You can get the X and the Y axis of the boxes, right? So this is how your annotation would look like. Class ID X, Y, W, H for the first bounding box. For the second one, you would get X1, Y1, X2, Y2, or some people also like to write X min, Y min, X max, Y max. Okay, okay. Okay. Okay, now what we'll try to do is we'll try to get the bounding box with this cat. What do we need? First, we know that this is a cat. I have encoded cat as 2 because in MNIST you had 9 digits or 10 digits. You encode it as 0, 1, 2, 3 or 1, 2, 3, 4, 5, 6, 7, 9. I have multiple objects. This object or cat is encoded as 2. In my scheme, this is 2. Now I draw a bounding box. So I know, okay, the top left corner of this cat is 278 pixels from the top left corner. So whenever we are doing this, the top left corner is considered 0, 0. And from there, you can get the X, Y. Similarly, you can also get the height and width of this, right? So this cat, okay, let's name this cat Luna. Luna gets this bounding box. So in this image, where is Luna? Luna is there at that bounding. So Luna at is here at this bounding box, red bounding box. Now we have this good boy doggo. We also want to annotate him. He also wants an annotation. Look, he's happy. So we get an annotation for this good boy as well. But I also have a canary. It needs a annotation too. So we give this thing an annotation. Okay. So every object of interest in the image gets an annotation. Now you will have two things. First is the image and the annotation which is stored as a text file. This text file will contain all the annotations of all the objects that are in the image. So basically we are trying to go through the basics of object detection from the basic principles of how we start from the image and how we make the annotations and how we work through it. Now I pass this image from an object detector. What outputs do I get? I get X, Y, W, H. These are what we have talked about. Confidence in class. Class is the class predicted by that for that bounding box, and confidence is the confidence for that class. So simple, like how we do for image classification. Here we would have had, let's say, if there were 5 classes, it would predict the highest class that has the highest confidence. Now, let's say if you train a classifier, so how do you know it's good? Like, you train a classifier, what do you do with it? How do you tell me, okay, I trained this classifier. How do you know it's good? What do you do? Yeah, you test it on a test matrix, right? You have a test bed and you test on it and you get some metrics. So maybe you use like precision, accuracy, recall, F1 score and such, right? The basics. What about bounding box? How do we do it for the bounding box? That is one, yes, but we need more, right? For example, let's say I train this first, let's say I have trained 2 object detectors. My first object detector creates this purple bounding box. So is purple a good prediction? What do you think? No, not really. Now I have trained another object detector. It predicts this blue bounding box. Is blue better? It seems to be better, right? It seems to be more aligned. So, but why is blue better? Like, how do you measure the fitness or accuracy of a bounding box? You need some method, right? So this is where IOU or intersection over union comes into the play. So what you do is you take the area of overlap and you take the area of union, and that is your IOU. So this IOU matrix could only lie between 0 and 1. So when there is a complete overlap, it will become 1. And when there is no overlap, it will become 0. Now generally IOU of 0.5 is considered okay. It's considered good for most of the applications. But depending on your application, you might want a higher IOU. It just basically depends upon what application you're working on. Now, how do you estimate true positives? Like once you have a bounding box, there are a lot of scenarios. Like if I want to calculate precision, recall for a bounding box, how would you do that? For example, in this scenario, I have an IOU of 0.92. I predict dog and the ground truth was dog. So how do you estimate true positives? So true positives, you need to have an IOU above your set threshold. This threshold you set. You could have set it 0.5 or 0.75. Depends up to you. It depends on your application. Now here, let's say if I have set IOU of 0.5, threshold of 0.5. Is IOU more than 0.5? Yes. Is the class level matches with the level of the ground truth matches with the class level of the predicted? Yes. So we consider this as a true positive. Now, here is one case where your IOU is above the threshold of 0.5, but your classes do not match. So this is a false positive. You predicted wrong. Now, my predicted label and the ground truth label, both of those matches, but they're not localized in the same space where I want them to be. So I again term this as false positive. Now you predicted dog, but there is no ground truth bounding box nearby. So basically you have predicted a box, let's say in air somewhere. So again, you have I don't know what you've done. So it's just false positive. Similarly, false negative. There is one ground truth, but you never predicted anything for it. So that's false negatives. Before we go there, like Do you think a notion of true negative makes sense here? Do you think that the notion of true negative would make sense here? Or how would you classify true negatives? Or do we even need true negatives? So let's think about it. What does true negative look like? There's nothing there. You're predicting nothing there. Right? So you won't be predicting anything there. And if you look into it, there would be, you could make, I don't know, you could make a permutations of boxes that would be true negatives. Right? So that generally don't make sense. So hence in object detection, we generally don't talk about true negatives. So every 2 cross 2 patch could be a true negative, 4 cross 4, 3 cross 3. So from 0, 0 so 1, 1 to W cross H, any box that could fit there could be counted as a true negative. Right. So we don't have control there. We generally don't talk about true negatives. Now let's talk about here. Let's say I have one image and I obtain these 4 scenarios. So all these 4 scenarios are within one image only. It's not like different images. In one image, I obtain these. What about the first one? What is this? What this should be? Where I predicted dog, ground truth is dog, my IOU is 0.86. So what is this? This is true positive. Okay. Now, thing to mention is my IOU threshold is 0.5. Okay. Now, what about the second one? This one. My IOU is 0.65. I predicted dog and the ground truth was dog. True positive. What about the third one? Where the ground truth is dog, but I don't predict anything. What about the last one? Are these correct? I think these are correct, right? So for this image, we can say we had a precision of 2 by 3 or 0.66. Recall of again 2 by 3, which is again 0.66. Now I change the scenario. Now IOU threshold is 0.75. What about the first image? True positive. What about second one? Does it remain same? Now what does it become? False positive. For example, so this is why I said your IOU threshold matters. So if you want to be highly accurate, so if you have an application where you do not want to deviate too much away from your ground truth bounding boxes and you want very precise localization, you could set your IOU higher to test the system more thoroughly. Again, yes, like you're talking about, the first is true positive, false negative, again false positive. Here your precision and recall, both of them have dropped from 0.66 to 0.33 and 0.5. Correct? Okay, this is good. Now I'll introduce this notion of average precision. Now what happens? So here, for each image, you get a precision and a recall, right? And let's say you have 99 such images. Now you can draw a graph out of it. This is the precision recall curve, right? Because if you look here, you have recall that goes from 0.2 to 1, so you can easily draw a graph out of it. Not a big thing. So here is precision recall curve. The area under it, under the PR curve, is termed as the average precision. Now introduce this weird term, which I always find it weird, mean average precision. Correct, because we generally mean and average means the same thing, right? What is this term then? So you do this for one class, and you can calculate average precision for class dog. Now you have average precision for class dog. You do it for all the class, dog, cat, bird, human, whatever classes you have, and then you mean them. So that's what it means when we say, okay, MAP, mean average precision. A lot of time we do an object detection, we come across these terms, we just don't know what these are. Now there are two more terms that we see a lot. MAP 50, if you have read any paper that uses an object detector, we come across this term called MAP 50. So MAP 50 is mean average precision calculated IOU 0.5. Similarly, you have to also need this MAP 50 to 95. What do we do here? So it's a mean over mean average precision. You get MAP at 50, you get MAP at 55, 60, 65, 70, 75. You keep doing it and then you have a lot of values and then you sum it up. Now we try out some hands-on. So I want you to open this collab file. So how many of you here have trained an object detector like a YOLO, REDTR? A few. I see 1, 2, 3, 4, 5, 6, 7 hands, 8 hands. Not a lot of hands, right? So, so remaining people, do you know how annotations get done? Like how would you get or obtain these bounding boxes? Yes, so we'll do that a little bit. So this is the collab file. If you scroll down a little below, so we remember the first session taken by Dr. Prakash, right? So this is the sort of application that you do with object detector. You can identify various objects in a scene and you can work around with these to make cool applications. In this collab file, if you scroll down here, you'll get this section, download dataset. Here you'll find that you can find this dataset here. If you click here, it will lead to this. I need you all to download this. It's a 3.6 MB file. It has around, I think, 146 images of a farm that contains some tomatoes. So our application will be counting tomatoes. So while we're at it, the file that you download, I also need you to upload it to your drive. We'll connect Google Colab to Drive and we'll use that dataset. So just a tip for the people who are using Windows, when you extract a file, it puts that folder inside another folder, right? So you don't have to put the outer folder, you need to put the inner folder onto the drive. Just be a little mindful. Everyone sees the dataset, right? They're able to download it. Anyone having any issue downloading the dataset or opening the collab file? This would be the contents of the folder. Also upload it to your Google Drive. Everyone done? So I believe every one of you have downloaded the dataset. Now we'll use this online tool from RoboFlow to annotate these images, just to get a sense how annotations are done or how do you obtain annotations for images that you have obtained. We click on get started. I hope I'm not rushing ahead and everyone is with me. You might have to create an account. I'll just use an account that I have. You can log in with Google, not an issue. So this online tool allows us to annotate datasets. So we can upload our folder here and we'll try annotating a few images. Everyone with me? So everyone has everyone reached to the RoboFlow page? You're getting? Okay, so you've created an account or? So same thing happened with me. Reload and maybe try again. Maybe try with another. So I logged in with another account, so it worked for me. Try that. So I tried with one of my account. It said timed out. Then I tried with another account and it worked. Hmm. Everyone with me? Is it fine? We're trying to create an account on RoboFlow so that we can try annotating. You can create a public data set, you can create a public project. It will ask you to drag and drop files to upload. What you can do is you can just put the test set here. I have my images from the test set uploaded to the RoboFlow. People having issues can let us know. We'll have TAs work you out. Can you guys check once? Sorry. You have downloaded the dataset. You uploaded onto RoboFlow. Now you say gets. So it would have said okay, get started or save and continue. Yes. Sorry. That is fine. We just want to showcase annotation process. How annotation gets done. You would reach, I think, somewhere here. Is everyone able to reach to this window? So those who have reached, they can click on an image and they can try annotating. Like this. This is an tomato. This is another tomato. Yeah, annotating. Start labeling. Assign to myself. At bottom. Yes. Click on any image and you can be able to. It gives you some instructions. Yes. You're trying to create a data set. We want to annotate. Annotate, yes. You have this thing assigned. So you have annotated everything. Why doesn't anything show? Can you do the process again? Show me what you were doing. You can delete that. So you have false. So you only need to upload images. Don't upload labels. Only upload images inside the test. If you upload the entire test folder, it also has the labels. So it will apply those labels. You only want to apply, only want images. Just take images. I repeat, you are only supposed to upload the images. If you upload the entire test folder, the RoboFlow gets the images as well as the labels. So RoboFlow thinks there is no point of annotating because we already have the labels. So it applies those labels on top of images. Anyone else wondering why we're doing this? Yeah, because next time you have to do a project where you don't have labels, how would you acquire the labels? Right. You won't always be given the labels, right? But what if your class is not in that auto labeler, right? So you are saying that you'll always be wanting to like localize objects that are there in RoboFlow. I think RoboFlow only most of the models have only 1,000 classes, which are the ImageNet classes. Sometime in the future, you may have an application that may require other classes. You have to sit down and annotate. RoboFlow is one of the easier methods. The other labeling tools are Label Studio, and you can search more about it. There are more tools to do the same thing. This, I find RoboFlow to be very easy and beginner friendly. So what we're trying to do now is just demonstrate the process of what people do. Like we directly use the data set, but there is a lot of human effort that goes behind. I think most of you are here, right? You have reached the page where you're able to annotate. So you can go back home, annotate, take a few images of your own or some other project that you want to try out, and try out annotating. We'll move on to the other steps. Like let's assume you annotated this, you got the data set. After annotation from this, RoboFlow allows you to download dataset as well. It will download dataset in the similar format that you have here. So you'll have a test set, you have a train set. So when you were trying to annotate, it asks you like what train test split you want to make. It randomly shuffled and made a train test split, right? This just downloads and very neatly segregates it into different folders. But we already have this annotated. Now we'll go forward and use this. So we'll now go back to the collab file and we'll try using a SOTA model called YOLO. How many of you have here heard of YOLO? Not the YOLO jargon, right? You only live once, not that one. The object detector model YOLO. So what's the full form of YOLO? Okay, so yeah, so instead of living once, it only look once. So we'll try using that model, and because the model libraries have made it very simple to apply machine learning tasks, this is a very simple library, very intuitive. You just need a data set and you need a data.yaml file. And ideally, this is how your data.yaml file would look like. It will contain where is your train set, where is your val set, where is your test set, very simple. How many classes, so NC is the number of classes you have, name of the classes. So as you make data set, the RoboFlow just makes it for you. Even Label Studio would make something similar for you. The last tag is just something RoboFlow attaches for itself, like where we downloaded its data set from. Because if you go to RoboFlow, so RoboFlow has its own RoboFlow universe where they have a lot of data sets. And they contain a lot of data sets. License recognition. So I think this is some game where the person is trying to count the cloud. What game is that? I've seen this. Just can't remember. The island one? So these are the annotations you'll never get from out of your auto annotator, right? You would have to sit down and annotate on your own for your own use case. So this exercise is to teach you how you can annotate your objects. Once you have the annotations, now how do you train it? Now we'll come back to our collab notebook and we'll use this very neat library, Ultralytics. This Ultralytics has very good models. You should explore it. It has YOLO. So just a quick question for everyone. How many versions of YOLO are there so far? 11? 13? 12? Okay. So you have YOLO V1 to V12, right? Then what about YOLO World? YOLO NAS? YOLO E? Right? There are way more models. So YOLO comes up, so it's sort of like an iPhone. YOLO comes up once every year. There's a new model of YOLO every year. They are just expanding, and YOLO is sort of a beta model. So we'll download this, like install this library, and we'll use it. So while this is downloading, or rather installing, let's do a quick recap. What did we do? We had some images, we annotated them, and then we acquired the annotations of them. We then have segregated them into perfect bins so that we could do a train, test, validation, split, whatever you have obtained. I hope everyone has uploaded that dataset that I gave you to the drive, because that is the dataset that we will use for training this YOLO model. So people who have already used YOLO or similar models, they might find it boring. But people who have never used YOLO or they had no idea what or how object detection works, this should definitely interest them, because a lot of research papers, or rather a lot of projects, directly use models like YOLO or RADTR or similar. Like in the presentation in the afternoon, they used a simple mobile net SSD network, and their project was basically identifying objects and then some analysis based on such objects. So these models are very powerful, and you can make really good applications out of this. Is everyone with me? People who are still on RoboFlow can come out. I don't want you to annotate the entire data set, right? You can do it at your home. I have no issues. Then we'll connect to our Google Drive. Google will ask me to sell my soul. I'll do that. Anyone having issues with the section setting up the dataset, let me know. Are you getting any errors like dataset not found, or no such folder directory exists, folder missing, or something like that? So I want to know if this cell runs perfectly fine for you. Everyone with me? Can we move forward? Okay. So now let's have a look at the data set. So I've written this function. What it does is it randomly picks an image from your train set and displays it alongside the ground truth bounding box that we have. Now, is this bounding box good enough, or like, could we have done something better? Any comments on this bounding box that we see on the screen? Is this okay? Could we have made it tighter, or should we have made it more big? Let's look at more images. We have a lot more tomatoes here. So if you ask me, I do not like these bounding boxes. Why? These are too big. Ideally, I want the bounding boxes to be as tight as possible to the object, not these bigs. For example, if we see here, there is a lot of space here. I don't want that. I want my bounding boxes to be as close to object as possible. But anyways, this is the data set that we have, and these are the ground truth bounding boxes. Now this is where we load the YOLO model. We'll be using a pre-trained YOLO model, and then we'll train on top of it. What is this process called? Anyone else wants to answer who did not hear what he said? What is it called? So basically I download a pre-trained model, and then okay. So is it fine tuning or transfer learning? Think again, is it fine tuning, is it transfer learning? This is a very confusing question that is asked in a lot of interviews. Okay, so here we are using YOLO V8N. So YOLO V8 is one of the models, one of the 12 or 13 models we were talking about, and N denotes nano. Nano basically means small, but YOLO every year comes up with various variants of its own model. So in nano, small, medium, large, extra large. Basically the depth of the model increases. The bigger the model, the more robust its performance, but slower the speed and more the space. For this application, YOLO V8 Nano is enough. So we'll be using YOLO V8 Nano. Now, training a YOLO V8 Nano is basically, or any YOLO model is a 3-step process. Downloading or installing or importing Ultralytics, getting the model, and this single line. YOLO model.train, data is equals to dataset YAML path. So basically you have to give the path to that YAML file that we're looking at. That just contains the test set and the location of the test set, location of the validation set. You have to set the epochs, the device that you want to use, the batch number you want to use, and such arguments. You can look into the Ultralytics library and look into what other flags that are there that you can set. So we'll just train this. It will do some check. It also prints the model. We'll let the model train now. Now these are the metrics that I obtain after my model has trained. So we basically trained model for 50 epochs, and my precision recall MAP 50, MAP 5095, all these metrics we talked about, right? We can try, have a look, how does my model work? Seems to be doing pretty well. So red is the ground truth bounding box, yellow is the model that we have trained right now. We can look at more images. Pretty good. And more. So do you find this image interesting? So red is the ground truth bounding box. Yellow is the boxes my model has predicted. So this means that my model is predicting objects which or what ground truth objects bounding boxes were not there. Right. So these green tomatoes were not marked, but my model has picked them up. So that is sort of like the noise. The annotator forgot to mark them. And there's also one more annotation somewhere to the left, which is just a mistake which my model has made. Now, who can tell me what are the use cases? Like we already talked about it, but what are the use cases for the object detection model? What can we do with an object detection model? Sorry, license plate, but beyond what we have seen. Like in this slide, we saw something in the afternoon as well. One was identifying cars, street signs. Yes, you can identify if there is any empty there's empty space in the parking lot. So if you have put it on a drone, you can count like here, you can count the number of apples on a tree, you can count number of cherries or something like that, right? You can also monitor your traffic. For example, look here, we can actually monitor traffic, the flow of the traffic, how many people are there, for crowd maintenance, like moderating a crowd so that there is not enough, so the crowd is managed properly. So this is what we had in store. We started from a wage classification. We talked about why classification is not good enough. Why do we need something more? And what that something more is, object detection, and how do we do object detection? We need annotations, and then how do we annotate, and how do you train a model? Now you have knowledge and you can go back and create an object detector of your own, right? So do you have any more questions here? Sorry? How do you identify? Sorry, how do you? Please speak up. Huh? Okay, YOLO overfits very quickly. That's a good question. So, what do you generally do when models overfit? So, best thing that people do is apply regularization. Correct? You can try augmenting it as well. Those are some methods to regularize it. And if you say my model overfits, sometimes, let's say for an application like Dr. Prashant was using in his application, I think even if it overfits, it works, right? Because it would have to run through the same streets again and again if it's overfitted for some parking signs. Will it give a lot of false positives? Yeah, true. I don't have an exact answer at this point, but generally you use regularization techniques. to ensure that model is not overfitted. Any other question? Okay, probably not. But there are some researchers, what they do is they enlarge the size of the image. So let's say if an object is, you're not able to detect an object in 640 cross 640, they resize it to 1280 to 1280. And the quality of image will reduce, but your model was not working initially. Now it has started working for at least something. Now, small object detection is an open research area, and there are people working on that. So YOLO is probably not made for small object detection. It is made for faster detection. Like the main thing with YOLO is that it is fast. So when YOLO V1 came out, it was able to achieve like, it never claimed that we are going to be very accurate. So I think state-of-the-art models who were very bulky were, let's say, were giving 80% accuracy. YOLO gave 75% accuracy. But those bulky models ran like 0.5 frames per second, and YOLO ran at around 110. So the major advantage of YOLO is speed and not the accuracy. But it works very well. As long as your object is big enough, it will work. But again, I reiterate, the YOLO was made for speed and not for accuracy. But the recent variants have shown remarkable accuracies. I have no idea if anyone has tested it out on small objects, but yes. One method is to enlarge the size of the object. Super resolution is also one method. So you feed it in the bigger images. So I think that is it. We'll close the session today. For tomorrow, we'll again be joining here at 9 p.m., right? I think yes.